today we see about 4 Maxwell's equation. Electric and magnetic field is produces time varying electric field is produces magnetic field, time varying magnetic field is produces electric field. So based on these relations, now we have to see the 4 Maxwell's equations. Okay, so first Maxwell's equation, the first Maxwell's equation is derived from Ampere's law. So here first Maxwell's equation is derived from Ampere's circuital law. So here the line integral of magnetic field intensity around the closed path is equal to the current enclosed in the path. The Ampere's circuital law first states that line integral of magnetic field intensity at any point is equal to current enclosed in the path. So line integral of h dot dl is equal to I. So here the current can be written as surface integral of current density into current density. So surface integral of j dot ds. So here we have to separate this current density into two forms. Already you know that conduction current and displacement current. So based on that concept, we have to divide this current conduction current into conduction current and displacement current. So conduction current density J can be written as Jc plus Jd. Jc is a conduction current density and Jd is a displacement current density. Already you know that conduction current density Jc is equal to sigma E and displacement current density Jd is equal to dou d by dou t, epsilon into dou E by dou t or dou d by dou t. You can substitute both values here. So line integral of h dot dl is equal to surface integral of sigma E plus epsilon into dou E by dou t into ds. So here sigma is a j and epsilon into dou E by dou t is a dou d by dou t. So here we can apply the Stokes theorem. You know that Stokes theorem, line integral of any vector around the closed path is equal to surface integral of the curl of that vector around the closed path. So we can apply the Stokes theorem to this equation. So line integral of h dot dl can be written as surface integral of del cross h into ds. So we comparing both equations, so we can get del cross h is equal to surface integral of j into dou d by dou t. We can eliminating surface integral on both sides, so we can get del cross h is equal to sigma E plus epsilon into dou E by dou t. So this is the first Maxwell's equation derived from Ampere's law. So the magnetomotive force around the closed path is equal to the conduction current and displacement current enclosed. So this is the first Maxwell's equation statement. So next we see the second Maxwell's equation. So the second Maxwell's equation is derived from Faraday's law. The Faraday's law states that electromotive force, magnetic force around induced in the circuit is equal to the decrease of magnetic flux linkage in the circuit. So V is equal to minus d phi by dt. So you can substitute the phi value here. So phi is equal to surface integral of B dot ds. So V is equal to minus d by dt into bs ds. So surface integral of dou B by dou t into ds. So line integral of E dot dl, we know that electromotive force can be written as line integral of E dot dl. So line integral of E dot dl is equal to minus surface integral of dou B by dou t. So again we have to apply the Stokes theorem. Line integral of h dot dl is equal to surface integral of del cross E into ds. So del cross E is equal to minus dou B by dou t, or B is equal to mu into h. So minus mu into dou h by dou t. So this is a second Maxwell's equation that is derived from Faraday's law. So the electromotive force around the closed path is equal to magnetic displacement current around the path. So from these two equations, the time varying electric field is produces the magnetic field and time varying magnetic field is produces the electric field. So next we have to derive the third Maxwell's equation. The third Maxwell's equation is derived from electric Gauss law. The electric Gauss law states that electric flux charge emerging through the any closed surface is equal to charge enclosed by the surface. So surface integral of d dot ds is equal to charge q. So d dot ds can be in terms of volume integral, it can be written as volume integral of rho v into dv. So that is equal to q. So then surface integral of d dot ds is equal to volume integral of rho v into dv. So here you have to apply divergence theorem. So surface integral of any vector around the closed path is equal to volume integral of that divergence of that vector around the closed path. So we have to apply this divergence theorem here. So we can get volume integral of del dot d into dv is equal to volume integral of rho into dv. So we can cancel volume integral on both sides. So we can get del dot d is equal to rho. So this is a third Maxwell's equation. This equation is derived from Gauss law. So the statements tell that the total electric displacement through the surface enclosing a volume is equal to the total charge within the volume. So this is a third Maxwell's equation that is derived from electric Gauss law. So next we see about fourth Maxwell's equation. The fourth Maxwell's equation is derived from magnetic Gauss law. The magnetic Gauss law says that magnetic flux through any closed surface is equal to 0. So phi is equal to 0. Phi can be written as surface integral of B dot ds is equal to 0. So surface integral of B dot ds is equal to volume integral of del dot B into dV. Now we can comparing both equations. So we can get del dot B is equal to 0. So this is a fourth Maxwell's equation and it is derived from magnetic Gauss law. The net flux emerging in any closed surface is equal to net magnetic flux emerging in any closed surface is equal to 0. So this is a fourth Maxwell's equations. Thank you.